Okay, welcome everyone. Today we have Christopher Gadzinski on giving us a talk on bit rates of very sparse superposition codes. I will share the link of the paper in chat. And right, let's start. Chris, thank you.
Yeah, thanks. So yeah, the title of the talk as advertised was bit rates of very sparse superposition codes. So that title is preprint that we have also in chat. But my plan for today, I didn't update in time the abstract, but my plan for today was to do this in two parts. So in part one, is going to be very general and generic and shouldn't be too surprising. I just wanted to talk about this really old classical idea of distributed representations. Um, and again, so I think this part will not be too surprising. I'm talking about things that have been known, for a while, but I don't know. I've noticed that there's not a tremendous amount of uh, I don't know. A lot of people don't know what distributed representations are or don't have a lot of, images of them in their head. So that's my agenda for this first part. And then in part two, I'll talk about this preprint where I basically take a really simple example, a toy example of a distributed representation and ask about its information efficiency, so its bit rate, how much data I'm allowed to store on it. And finally, this leads to some speculation. I have one last slide on speculation about what this means for sparse autoencoders and cross-layer transcoders and stuff. Okay, so first problem I want to talk about is how do I encode a point? Let's say I have a point on the plane, or maybe I have a point on the torus, and I want to encode the position of that point with a vector of bits. So the standard thing you do on a computer is you use a place value encoding. You'd allocate, 1 bit. You'd first say I want to store the x coordinate and the y coordinate, and you'd use, 1 bit for each bit in the binary representation of the coordinate. Kind of on the other end of the spectrum, you could use what's called a local code. So, basically a one-hot encoding of the point. The idea is that these squares here are bits in my code, and what I'm drawing is the points on which that bit is active. And somewhere in the middle, somehow, maybe conceptually between this local code and the place value code is a coarse code, where I associate each unit, so each bit in my code, with a region, so a relatively large region on the plane. And the idea of a coarse code is that when you give me a point, I write down zeros and ones corresponding to what regions contain or do not contain the point. So how good is a coarse code? Well, it's a little bit better in information efficiency than a local code, but generally not as good as a place value code. And for example, if I ask how good is a coarse code on this, particular example of storing a point in the plane, one way of thinking about this, there are different ways of thinking about this, but one way is to think about this old combinatorics problem of how many regions do I cut the plane into if I draw a bunch of circles. And this grows like a quadratic polynomial with respect to d, my number of units. In general, if I do this in higher dimensions, what I'll find is that at first, the number of regions that I'm allowed to distinguish grows exponentially. And then after a certain point, I start slowing down. And asymptotically, I'm only a polynomial of degree d. So overall, okay, the course code sounds like kind of a weird strategy. It's sort of efficient if I don't need much accuracy, right? So if I want to get a lot of accuracy in my point, I have to add lots and lots of very subtle fields. But they're decent if I don't need much accuracy or from very high dimensions. Another cool property of coarse codes, which is not true for local code or the place value code, is that they come with a really natural notion of similarity, right? They act like a nice embedding to do linear regression on. And so I'm not going to think too seriously about this, but let's say that I have let's say D is my distribution of micro features. So little features. So in this case, the micro feature would be like a random receptive region, a random circle on the plane. Well, I can make a course code by just taking D independent draws and putting them together. So I take D draws, and then that's my course code. I fix that randomness in advance. And then if I want to encode two elements, X and Y, in my domain, the inner product between those two vectors is proportional to an approximation of the second moment of this distribution on X and Y. So just something to have in mind. And in fact, in general, so this weird idea of just grabbing random features and using them for an embedding is actually a smart idea in practice. It's like there's a very old paper on like random kitchen sink for like kernel regression, and there's like this idea that if I have a high dimensional data set, I can randomly project into low dimensions. It's just like a relatively good embedding. And to make this visual, so here is this function kxy, or rather, really this function inner product cdx cdy. So cosine similarity of vectors for these two representations I was talking about. So if I take the local representation and I ask what's the inner product between the encoding of one point and the encoding of another point, well, it's 0 unless they're very, very close together, right? If I take the place value encoding and I take the inner product or cosine similarity between two bit vectors representing 2 points, I get something kind of strange. And if I do this with circles, if I use the coarse code and I take cosine similarity of coarse codes, I get this thing which should, converge to a nice kernel function. Really the second moment of this random process that I'm using to make the code. Another fun thing to keep in mind, so just a litany of little facts about coarse codes at this point. But if I take my this coarse code and I do PCA, so I generate a bunch of points on the torus, I send them through my code, I get a bunch of code vectors, and I look at the principal components as functions on the torus. There is a relationship here, right, between I'm going to have a relationship with irreps of the torus. So like the first 4 will be these nice like combinations of sign in one dimension, sign in another dimension. So when you do PCA on an embedding and you see, oh, I have like circles or I have like a manifold, a coarse code is one very natural way to get that. Okay, so that's coarse codes. Let's consider a new problem. Let's say that I don't want to just encode one point, I want to encode a pair of points. If I'm doing this on a computer, there's really only one thing I would consider, right? Which is, well, I have one point here, I have another point here. I should, I have a decomposition in my system. I should use that decomposition to make my life easier. And I'll use, the first number of bits of my representation to store the first point in the next however many bits to store the second point. And on computers, I would call this a local representation because each bit here, each unit of storage is tasked with storing one component of my system. And there are very, very few exceptions, I think, in computer science where we don't basically use local representations. A few examples I can think of are linear sketching and Bloom filters. You very rarely do the situation where I have 2 points and I use like totally entangled representations. But if I'm looking at coarse codes, there's a really natural thing to do. If I have a coarse code for X and a coarse code for Y, it turns out that adding them together is a good code for the pair of points. And so not to I'm just kind of looking at the images to see reactions that people see. If this is surprising, something I should explain, or something that is like, yes, obviously.
Yes, please. Could you explain?
Okay. Yeah, so I mean, one way you can think of this is look at this image here I have, right? This is what happens. This is the function. So I'm fixing a point X, and I'm looking at cosine similarity of the embeddings of other points with X. And this is like, a field that's concentrated at that point. So I can identify the point from its embedding in this way. Now imagine that I took x and then I also took y. Then now this function would become something which has two peaks, one at x and one at y. And so it's intuitive that for sufficiently large D, if I have enough dimensions in the course code, this is a faithful representation. Another way of saying this, there are actually a whole bunch of properties which are equivalent. Another property you might want of a course code is that for sufficiently large D, I can approximate many functions as linear functions of the course code. And another thing I might want to say is that the second moment is strictly positive or is positive definite. So there's no set of points, x1, x2, x3, and so on, so that the second moment evaluated on those points, so the matrix of second moments is rank deficient. And all these things are equivalent, right? And all these things are very, very common, right? So if I make a course code by taking like a linear function and then an activation, this will generally have that property, except for very special activation functions. This also kind of leads into, so I'll talk about a little tiny bit about compressive sensing later. And in compressive sensing, we would call this kind of property, where I have, this property of map CD that tells me if I have distinct elements x, y, z, that the images CDX, CDY, CDZ, that these are nicely linearly independent. I would call this an incoherence property. And one more example of the code for which this is true. What if CD, imagine that CD were the symmetric tensor power? Then now this is an algebraic geometry fact, right? That a set of points is encoded by the sum of symmetric tensor powers of sufficiently high degree. So just another connection to throw in there. Well, okay, all good. So I'm talking about sums of course codes. I have alluded to in my introduction that I'm interested in like sparse autoencoder stuff. And when we talk about sparse autoencoder stuff, we're talking about the superposition hypothesis that maybe I'm representing a number of things as by summing feature vectors or something, all very speculative, all very weird. Well, what kind of crazy, outlandish 20 billion parameter system would sum together course codes? You don't really need to look very far. So what if I do linear regression on a course code? I'm going to try to build a model phi of x by having some matrix, multiplying it by a course code on x. And now let's learn some relationships. What happens when I learn these relationships? Basically, what's happening if I do gradient descent or some related method is I'm adding some products, zi tensor course code of xi, to the matrix W. These are like gradient descent directions for W. And I can kind of say, and this is a little bit weird maybe, I'm not sure if you often think of it this way, but I can see the matrix W that I get from the training process as kind of a weird, it's a representation of the memory that when I got xi, I needed to move in the direction zi. And in practice, if I have lots of data points and I don't have many dimensions in my course code, this will be a very, very fuzzy memory. But imagine just, as a thought experiment, if the dimension D of the course code is sufficiently large, this is actually a faithful encoding. This matrix W I get from training is a faithful encoding of this fact, of this memory, this information that when I got xi, I moved in the direction zi. It's also worth thinking about the fact that the fact that memory is lossy here is kind of a feature, right? Because this means that when I update on xi, and I want to move it in direction zi, this also automatically moves me. This also automatically changes my prediction for other points which are similar to xi. So what I'm describing here is just linear regression on some feature space. This is like not exciting at all, but I thought it's a kind of cool example of this scenario of adding together course codes to represent a system of objects or a set of objects.
Can you explain the generalization again? Why does what you say not happen without the course code? Why is
Sure,
what
yeah.
why is what you say kind of a property of course code in
Yeah,
some
so if I use the local code here, so first of all, if I use the place value code, I have no idea what would happen, something weird. The place value code is very strange from this point of view of cosine similarities, right? But if I use a local code here, what would happen is that this product here, adding this product to the matrix W, would only influence this model when its input is very close to this, right? Because when I pass something through this model, what's happening, if W is a sum of things of this form, the output of the model, um, yeah, is a sum of things of this form and then multiplied on the right by the input I gave it. Yeah. Yeah. So this is yeah. So I'm not sure. I hope that's clear now. Yeah.
that's
There's also this other whole picture of that I'm realizing maybe isn't super universal, that doing gradient descent, training this model with gradient descent for large D is the exact same thing as doing something involving a Gaussian process, as the computing the maximum a posteriori estimate of a Gaussian process on some data, where the kernel of the Gaussian process is given by the second moment of the micro features that define the course code. Okay, so let's step back for a second. Imagine that we're back in the 1970s or whatever, and your job is to make a system that learns associations. Maybe it's super simple associations, right? Just imagine this case of like regression, right? I want to learn that these points over here are bad and these points over here are good or something. There are a few strategies that kind of come to mind. For example, maybe I realized that, well, I can just store all the data I've ever been given in a database, one row per data point. And then when a new data point comes in for me to do inference on, I'll, do k nearest neighbors or apply some sort of fuzzy inference rules on the fly, use some sort of fuzzy logic. And that would call this is a local representation for data points because the way my system is structured, I can look at it and see, yeah, that area there, that's dedicated to this one data point. And that's dedicated to this data point and so on. Another strategy, which maybe is natural, is to have some way of decomposing the relationship I'm expressing into nice rules, like, and like an expert system or something. And then my learning process is now, instead of adding points to a data set and doing inference on the fly later, now it's adjusting the rules as the data points come in. But this I would call a local representation for inference rules. I zoom into the system and I look at a part of it and I say, that's the part of the system that's describing, what happens when I get a point which is kind of up there but not too far down there, and so on. And this third possibility, training a shallow model, like a linear model or a bolt-on machine or whatever on course codes, is kind of qualitatively different from those two other strategies. Because I can maybe interpret it in terms of remembering data points or in terms of learning a function with certain properties. But when I zoom into it, when I actually look at it and I ask, where are the data points? Where is the description of my function? It's kind of mixed up everywhere at once. And so that's the essence of what we mean, what I mean when I say a distributed representation. In preparing this talk, I took some time to look over a few references to see if everybody agrees on what distributed representations are. It turns out they don't. It's a very contentious term, a very weird kind of subjective term. There's no definition. And I think it becomes clear when I try to write out the definition. I would say a distributed representation is the scenario where the conceptual parts that I would divide a system into are many to many, whatever that means, with the mechanical parts that actually do the work. So, or in other words, under a microscope, so if I zoom into this lowest level, many different components or mechanisms or concepts share the same hardware. And the big problem with the definition, of course, is what do I mean by component, right? What's a conceptual part of the system? That's a matter that's in many cases that's kind of up to subjective interpretation. Maybe sometimes you can argue there's like only one natural way to decompose it, but in general, that's not going to be obvious a priori. And here's the image I have, going back to this example of storing 2 points. I would say that the thing we do on a computer, using some bits to store the first point and some bits to store the second, that's a local representation. And this weird thing of summing together coarse codes or making a coarse code whose micro features are features of 2 points simultaneously. This is a distributed representation. And this is this term that I had to discover for myself reading those books on parallel distributed processing from the 1980s. And it just feels like if deep learning were like an actual science, that you would learn, this would be like you'd have a course in like first year of like deep learning studies. It's like distributed representations. And you'd be like, yeah, we're on the same page. But as it is, you kind of go around and you realize that everybody kind of disagrees about what these things are, and nobody has a picture. For example, nowadays, when you look in the literature, you look at like Chris Ola's blog posts, and you see what people think distributed representation means nowadays. There are kind of two effects that people have been noticing. And one is that sometimes you have systems where there are more components than units of hardware, or there are more components than concepts. And this is old hat. When I write an integer down using a place value system, I can write exponentially many more integers than I have, bits to store the integer with. Like, yeah. And distributed representations have their own version of this, right? Well, one thing we'll talk about later, I won't really talk about it much. I'm going to breeze over it. But if I choose random vectors in high dimensional space, these kind of act like different symbols, right? It's like I'm taking hash codes, like I'm taking hashes, very likely to be very distinct. Another thing, though, which is a little bit more special, doesn't happen with computers, only with neural networks, is this idea of compositionality, or, well, I don't know if I can really say that, but anyway, another thing that people sometimes mean, if you look at the Word2Vec paper, for example, it has this title like distributed representations for something, something words. And I think that what they mean by distributed representation might not be this, or what's on my previous slide. For them, it's possible, Chris Olah seems to think so, that when they say distributed representation, what they really mean is that the meaning of a word is distributed over different concepts, right? So they're not really thinking about like being distributed over numbers. They're thinking about being distributed over concepts. And they're thinking of this example of, king and queen having like one like concept in common and another concept like, different.
Why is that?
I don't really agree with that
Why is that?
meaning of
Why is that different? Like the additive property seems to match what you mentioned before. And each component of the vector, like I guess each not component, but there are directions of the vectors that sort of specify different concepts slash components. I guess like is the disagreement here what components means?
Yeah, like the disagreement, I guess the disagreement here is what the hardware is, for them it's like they're thinking of directions as like the hardware, and I'm thinking of, the hardware is really, the neurons or something.
Right.
Yeah. Anyway, not to make too much of this distinction though. I think we're all talking about very similar things. Okay, here's a big table I made. I don't know how long I want to take to go through it. How am I doing for time? About halfway through the hour. Okay. But just some examples. When I represent a data type on a computer, I would say I do this with a distributed representation. What are my components here are the different values of the data type, maybe. And the things I'm using to store are the different bits. right, in its representation. And this is, this is a distributed representation. You can't say computers don't use distributed representations. But where things become more local is where I think about like the structure of programs. So if I look at a program running in memory, I can look at different variables, and these have like different meanings. And different variables are stored at different addresses. They don't interfere. And same thing with programs or subroutines, right? I can point to a specific address in application memory and say, that's the beginning of this method which does X. And that's another local representation. This example I gave of MLPs, the components to represent are learned associations. And I would say that if you're using a course code, you should have distributed representations, right? So different memories are represented using the same in superposition over the same weights. Not everybody in machine learning thinks that neural networks are supposed to be distributed, though. You'll see people thinking about like very sparse NLPs. And for them, I feel like the picture in their head is that inference rules are supposed to be local. I'm supposed to be able to point at that neuron and say, that's the neuron that kicks in when I'm in this mode or that mode of the data. There's this example of words effect, which I mentioned before, and it's kind of distributed in various different senses, right? So I can say either maybe my components I think are words, and then it's obviously distributed because I don't reserve special dimensions of the vector space to represent different words. I represent them all in superposition somehow. I could also have a more sophisticated idea of what the components of the system are supposed to be. Maybe I have like atomic meanings of words that are composed together to make words. And this, we would think about whether it's also distributed, right? Is it also true that dimensions in my vector space do not really have specific meanings, even in the true decomposition of the system? And at the end, I have some kind of weird ones. So, if I look at a memory in my brain, do I think that two different memories are represented in isolation, like kind of not entangled, or if they're kind of overlapping and using the same hardware? And there are a lot of informal observations to suggest that probably the representation we have for memories is somewhat distributed, right? And yeah, and if you look over, there's lots of interesting things from the 1980s and 1990s on the advantages that people thought distributed representations would have. Some of them I've already alluded to, this deal of like automatic generalization, which is also related to kind of this idea of content addressable storage. And one really, maybe the property, the distributed representations that's hardest to model, and the one that I have the shakiest understanding of, is that they can adapt in ways that local representations don't do so easily. So if I'm looking at some problem where it turns out midway through training that I'd really like to introduce an intermediate concept, maybe a symbolic system would have to make the decision to add a symbol, to allocate a new symbol or allocate a new region in memory. And one of the advantages of using distributed representations is that I don't have to do that explicitly. I can and I would have loved to show like a simple toy example of this, but of course there are whole conferences named after learning representations. So I hope I can leave this to your imagination. Okay, so that was the general talk on distributed representations. And part two, we're going to zoom in on one very special distributed representation and ask some really, really simple questions about it. So my motivation comes from this. Do I have two slides switched? Da, da, da. Okay, all good. So my motivation comes from this mechanistic interpretability stuff, where we have some big model and we're looking at activation vectors inside it. And they can be activation vectors from just one layer or drawn from multiple layers or whatever, all over the place. And we want to kind of decompose the model into circuits or understand what kind of computation it's doing somehow, all very, very vague. But certainly one thing we would like is to understand what these activation vectors mean in the first place. What's the data they're carrying. And I don't really have time to go over what led us to this hypothesis, but some people started to think that maybe you can model activity inside a neural network as a low-dimensional projection of a much higher dimensional but much sparser signal y. And so I think most people here are familiar with like the sparse autoencoder stuff. Can you like raise hands or yeah. Okay. So you know that the approach we have to do this to try to learn what I need to learn is this matrix B and also how I infer Y from X, right? And the assumption we make in sparse autoencoders is that it should be good enough to basically choose some matrix A so that Y can be inferred from X. So this high dimensional Y can be inferred from X by mapping under A and then thresholding or something. And we try to train this kind of this autoencoder model. One thing that really strikes me about this work is we're not even sure like what we're looking for in the first place. It's very, very kind of open-ended and weird. We don't know what a feature is supposed to be. Is it supposed to be a Boolean? Is it supposed to be a continuous variable? Is it like a point on a manifold? So I think we should start by asking, and in my head, I feel like one good approach is to start asking really, really simple questions. So first, how much information do we expect to find encoded in the activation vector? If I had a sparse autoencoder that worked, how much information would be in this latent sparse variable y? And what I did in this preprint is I supposed that the linear superposition hypothesis was true, and I looked at a really, really simple example where I just have binary features, and I just asked, how good is this, random linear projection at storing this vector? So to be specific, what I'm doing is I'm taking a very large n, say on the order of 1,000,000 or 1,000,000,000, and I'm thinking about the problem of encoding a very small subset of k elements in this very large set. So k here is about, 256 or whatever. And the encoding that I'm looking at works by associating each number in this very large set to a vector in r to the d, which I'll call a code word. And to represent a set of k elements, I'll just sum together the code words. This is what sparse autoencoders think. This is the hypothesis that underlies this linear superposition stuff. We think that there are these like code words, these special patterns of activation, and then an activation vector is an encoding of a very sparse signal over this very high dimensional space that's just a linear projection. And the question I want to ask is how large does the dimension of the code word, the dimension of this code need to be as a function of n and of k for this to be a good encoding, for it to be possible to decode this sparse latent from this projection? So of course, this depends on what strategy we choose to decode it. In some sense, like if I choose generic vectors in RD, I can always, decompose it if I have infinite precision, but whatever, that's not interesting. Here's another simple little reminder. Let's think about the problem of inferring just one coefficient of my sparse vector y. I'm going to ignore all of the other coefficients. There are exponentially many of them. There are way too many. I'm just going to focus on one. And in that case, my code, it looks like some unknown scalar times a vector plus some sort of noise. And we know from the theory of like linear filtering and whatnot that the optimal solution to this problem is to predict S based on a certain linear function of X, which I call the matched filter, and denote lambda, which depends on V and on the covariance of Z. And under the assumption that Z is Gaussian, this is the best I can do. And so if I say I have a vector and I have, some scalar, which maybe is 0 or 1 or whatever, I know this vector V and I'm adding some Gaussian noise, the best I can do, it's easy to solve this problem. The best I can do is just take an inner product with lambda and then threshold. If this inner product is less than something, I'll say that S is 0. If it's larger than something, I'll say it's 1. And so this is what sparse autoencoders do, right? And just to make things concrete, here's like another illustration. Let's say I use D equal to 128. So I'm using 128 dimensions. I want to encode the set A, B, C. And what I do is I choose a random vector for A, a random vector for B, a random vector for C, and I add them together. And the nice thing about random vectors in high dimensions is that they tend to have pretty small inner products. And in this case, it turns out that if I choose any other random vector in 128 dimensions, feature D, let's say, if I assume it has unit norm, and I take an inner product with this sum, then there's a pretty high probability that it'll have less than 1/2 inner product. And that's sort of okay, but it's not that great, right? I'm using 128 dimensions. It should take just 20 bits to encode a million things. So I should be able to encode a set of 3 things drawn from a set with a million elements using only 20 times 3, 60 dimensions if I'm using 1 bit per dimension. So the fact that in 128 dimensions, it's already kind of iffy to encode a set with 3 elements means that something's a little bit weird, right? I'm a little bit disappointed in my random vectors. Here's an image of what this looks like. So going back to our example of the points, just to make things nice and pretty and visual, let's say that I want to encode a set of 4 points in the torus. I take my course code or whatever, random vectors, course code, anything works. I sum them together and I get this code, which is supposed to represent this set. This here, this is that function I was telling you about earlier. This is this function that, given a point on another point in the torus, tells me the cosine similarity of the course code of that point with this code of the superposition. And you see that here, actually there's a lot of covariance between the components of my course code. And so this is not a great filter, right? Like I can kind of vaguely make out the shape of the points, but if I just thresholded this thing, I wouldn't get a very good result. If I correct for this thing, if I use match filters, I get this reconstruction, which looks a bit better. I kind of have some little pricks of green in a sea of like light green and light pink. And then if I threshold this, now I'm able to recover more or less this thing I started with. Okay, so just to jump straight to the answer, I could have multiple slides on talking about how cool Johnson-Lindenstrass is, but just to jump straight to the answer, how many dimensions do I need to reliably encode a k-sparse subset of a set with n elements? The answer is about 8 times k times log of n. And this 8 is very, it's really an 8. And here you see some empirical confirmation of this, because when you derive this kind of expression, you do all these sorts of inequalities on tails of Gaussians and whatnot, and you are not really sure how much exactly you left in the slack in your inequality. So I did an experiment and I saw I was not too far away. Each column here is a different value of big N. You can focus on the top row for now. The top row uses threshold decoding, where I take inner products and I just see whether they're larger or smaller than 1/2. And what I'm showing is that for each value of n, as I increase k, the required number of dimensions grows about linearly in k. And the slope of this line grows, it's pretty well modeled by, so 8 times log of n. If I write this in the base 2 logarithm, I see that thing I was talking about before. I get 5.5 times k log 2 of n. So in other words, I need 5.5 dimensions to encode each bit at best, which is a little bit disappointing, I think. If I use the more recent sparse autoencoders have used top k activation, where instead of using 1 cutoff, instead I go in with the assumption that my sparse code my sparse latent has exactly k active elements, and I choose the cutoff that will leave me exactly k active elements, right? So I choose the top k largest inner products. If I do this, this factor goes down. It goes down to 4k log, except I have a little extra term here. I'm going to have 4k log k. But still, this is not, not so great. One thing in this graph is I've done something a bit silly. In this first column, I'm saying that I'm encoding with large N equal to 2 to the 8, so 256. I'm encoding subsets of a set with 256 elements. And I'm talking about requiring like 1,000, 2,000 dimensions to encode this, right? Well, that doesn't make any sense because I can encode an arbitrary 256 dimensional vector using a 256 dimensional vector, right? So this graph is clearly not showing the what is possible if I chose my code words intelligently. I'm choosing here in this graph, I'm choosing them randomly. Maybe things would be better if I optimized them. And you may be aware of this like work by Anthropic on like toy models superposition. They did a lot of work on optimizing code words and whatnot. But one interesting fact that I uncovered doing this work, which I have no mathematical explanation for, but kind of feels intuitive, is that if I ask, well, I have to go back here and first remind you that basically what determines the performance, what explains what's happening in this graph, it's not like maximum inner products between code words, it's the scale of inner products. It's a typical amount of noise I get when I take an inner product with a superposition. And if there were a way to make this, so this is very informal, if there were a way to improve this in general, it would require choosing a dictionary of code words that whose inner products have smaller scale on average. And so I set up this optimization problem of looking for a dictionary of of D code word of N code words in D-dimensional space. And I try to minimize the variance of the inner products between distinct elements. And for example, with N equal to 64, so I'm looking for 64 different code words, what's the optimal scale of interference I can get? Well, when my embedding dimension is greater than 64, of course this goes to 0. This is on a log-log plot, so it drops off asymptotically. For dimension less than 2 to the 6, less than 64, it's somewhere between this dotted line, which you can just barely make out, which is the scale at initialization. So it's going to be 1 over square root d or so. It's going to be somewhere between that and 0. And if you see these nice curves that you get from choosing larger and larger dictionaries and trying to optimize the scale of interference. If you put all these curves on the same graph, if instead you graph the ratio, so d over n, and graph it against the ratio of the improvement of the scale of interference, and I don't know if I'm explaining this super clearly, but anyway, you have a kind of a regular property that holds for all values of d and for n. And the takeaway from this is something which I thought a priori was intuitive, which is that when the number of dimensions you have is a small fraction of the total number of code words you want to represent, there's basically no benefit to optimizing from the point of view of minimizing expected scale. And also, I really have had a lot of trouble finding literature on this. People study a lot sphere packing, which is kind of equivalent to finding a dictionary with minimum maximum inner products between vectors. But that's not what I care about. If you look for those bounds, you get stuff that's much, much worse. I want scale of inner product. And I have no idea what the answer to this problem is. I did this with gradient descent and kind of confirmed my intuitions. There's also one more problem. I have so far said that I don't like this 5k log n because the constant term is pretty big. But remember that we're not encoding an array, we're encoding a set. So even if in general I could encode a set with ck log n dimensions, the bit rate, the number of bits per dimension would still be really small because the true entropy of the thing I'm encoding is log n choose k, which is more like k log n minus k log k, right? There's this extra term I'm forgetting because I can rearrange my set, and my encoding doesn't contain this information, and so I shouldn't be paying for it, right? So anyway, if I just go through this computation, I look at the bit rate that I would pay to store a set in ck log n dimensions. I find that if the ratio of k over n is greater than some epsilon, as n goes to infinity, this is a catastrophically bad strategy. Because it's as if I'm paying for the order of the order of my elements, and I'm not encoding that. On the other hand, for when k is very, very small compared to n, so when log k is a small fraction of log n, okay, I can no longer make this claim that I have, actually catastrophic inefficiency. I just have some constant factor of inefficiency. I'm realizing I'm going very fast over this part, but maybe if there are any questions, or we can talk about it later. Anyway, just to get to the punchline here. Okay, there's compressive sensing. I want to leave some time for comments, so I should just jump to the punchline, which is that here's a super simple algorithm you can do instead. Instead of just taking all my inner products over all code words at once and looking at which ones are largest, how about first you just find the one code word that has largest inner product and assume it's in the code, and then make your life easier by removing it from the code and then looking for the next code word. That makes sense. So this is an iterative method. How well does this method work? Way, way, way better. And if you put them on a graph, so this is how, for the case of n equal to 1,000,000, this is how many dimensions threshold decoding needs as a function of k. This is how many dimensions this top k decoding at sparse autoencoders need. And this is how many dimensions that super simple algorithm that I mentioned, matching pursuit, requires. And what's really interesting about matching pursuit is it's kind of close to using about 1 dimension per bit. It can encode 1 dimension per bit, right? Threshold and top k have this property that as I increase k, the dimensions per bit I'm paying diverges to infinity. And in this classic regime of compressive sensing, which I haven't even talked about, that's kind of the case where I'm all the way, I'm way, way, way past the right of this graph in a regime where k is a fraction of n. You wouldn't even consider threshold and top k because they're just ridiculous. But when k is very small compared to n, it's interesting that these strategies are kind of competitive. They're kind of in there, but there's still a big gap with what should be possible in terms of information density. I promised also a slide on speculation. Maybe it's best to leave that for later. First, I get questions and we see reactions, and then I talk about what I think this means for interpretability. Yeah, I think I'll stop here.
Yeah, thanks, Chris. Yeah, some questions, and I definitely want to look at the speculations and round of
You're
applause.
inviting the first question to be like, what is the application to interpretability?
Yeah, so the application to interpretability is not really straightforward. I'm not saying oh, we should go in and replace sparse autoencoders with matching pursuit decoders or something. The application to interpretability for me is more conceptual. It basically just comes down to this question, right? There's a problem people have been looking at, right? That even as you scale sparse autoencoders up, even if you add more layers and do transcoders and scale the number of latents to ridiculous sizes so you can barely compute them, you still are left with this so-called dark matter, right? This stuff that just doesn't seem to be modeled by these approaches. And so the relevance of this picture, this story I've told to interpretability is just in asking this question, which is, are we sure that it's impossible for features to still function below the noise floor that limits linear decoders? And the picture that I like, the kind of the thought experiment that I like thinking about is, I mean, I started this talk talking about distributed representations, right? And we are now on, people are now on board that, yeah, you should think of an activation vector. You should think of a single activation in in an activation vector as not being a feature, but as being some sort of entangled, mixture of many facts about different features. But we seem to be very scared of the idea that computation can be distributed, right? When you talk with interpretability researchers, they say, well, it doesn't make sense to have a feature that I can't read. And sometimes that makes sense, right? If I do an attention circuit, it's very important that I'm able to pick up on features using an inner product of a query and a key, right? So some features, it's nice when features can be read in simple ways. But couldn't there be something like a distributed representation for computation, right? Is it really necessarily the case that a feature to act in a circuit has to be read by some neuron and then printed out to another neuron? What if I took some sort of latent sparse object Y, took a linear projection, now I have a code, and then had a decoder map that were able to recover Y from this code, even though some of the features of Y are below the noise floor, are not legible by matched filters. Well, so if I take Y, so projection and then decoder, I end up with Y. What if I apply some perturbation here before decoding it? Depending on the nature of the projection, right? Depending on the nature of the code words I'm choosing, and depending on the nature of the decoder, surely this can express some sort of interesting functions without being locally represented, right? So without actually being able to see the computation of features happening in this step. And so it's not really an application, it's kind of just a conceptual, possibility that I'd like to put out there. I have no idea how you would read or deal with these features. That is a hard problem. But you can at least look at toy models. I think one like maybe more tractable problem is like, can you exhibit a toy model where computation happens involving features that are apparently inaccessible?
This reminds me of the sort of computer science trick of swapping the values of two variables using the XOR, like without a temporary variable. Like if you allocate space for two variables and then you XOR them and then subtract them in the correct order, then you swap the two variable without using a temporary variable, and then the intermediate computation is like entangled.
Yeah, I guess there is one example, that's right, of entangled. Yeah, if you XOR two things, if you take one thing and then XOR.
Yeah.
Yeah.
And I guess you can like XOR something together, and then like those, as long as at the end of the computation you remember to disentangle it, you get the result. Maybe that can be implemented in a network. And
yeah, well, but I think the problem though with the XOR is that at each step you're still like just one step away from the result, right? So even at the step in the computation where I have X and XOR Y, I don't know, I still have basically two things. I think that the kind of examples I was thinking about are like this graph here. So I think that this thought experiment I'm describing doesn't work for just subsets, for just totally generic things. I think you need to have some structure.
Yeah.
And think about this scenario. I start with the signal. Here's my sparse signal, some sort of geometric thing. I project it into this code, which is kind of a weird representation of it, and it takes a little bit of. Okay, in this case, it actually was very easy to decode. I just applied linear and then threshold. But in some cases, I have to do a little iterative process. I have to take matched filters, and then I threshold a little bit of it, and then depending on what I observe, choose a different filter. Another thing I didn't mention is that this matched pursuit thing, it looks like not a very practical thing for a neural network to implement, but it becomes much easier when you have any sort of assumptions about the data you're storing. If I think that my sparse latent signal Y has like some sort of hierarchical structure, so like this part of it is only active when that part is active and so on. I didn't really talk much about this idea of adaptive filtering, but basically the idea is to, oh my gosh. But basically, the idea is to, instead of just applying one linear filter, first you measure something and determine what situation you're in, and depending on that, apply different filters, right? And so imagine I have some sort of example like that with some sort of structure up here and some sort of structured decoder down here. I mean, can't you imagine that like some sort of perturbation here, that some perturbation, some simple functions involving the code would kind of parameterize in a distributed way maps from the signal all the way to its reconstruction? I don't know. This is a thing I was working on a few months ago. But it requires a lot of.
I mean, sorry, I interrupted you. I was just going to comment that this reminds me of, I don't know if you looked at how quantum error correcting codes work and like operating on encoded qubits. The torus thing reminds me of it because one of the most famous the topological error correcting codes encode qubits in terms of homology cycles on the torus. It's a sort of very complex encoding, and then the simple operations that you want to do, the gates, in terms of the actual underlying physical qubits, very, very, very complicated operation. So yeah, this kind of encoded simple operations at the abstract logical level that are encoded by very complex operations at the physical qubit level or at the sort of activation level. But that's an example, I think, of something that would, in principle, be extractable by kind of that's an example of a linear representation sort of hypothesis thing where you have the simple thing at the level of the learned representation. That's like much. I guess I don't really understand what you're getting at with this distributed computation thing. Could you go back to that slide and like what are you saying? You're looking for something that yeah, could you repeat what you're looking for?
I guess I'm kind of looking for the opposite. So yeah, normally the story is you find features, you find a representation where the operations you want to express are now simpler to express. And what I'm talking about is a situation where you find a representation so that simple operations have not so simple or not so obvious interpretations in terms of underlying features. It's a very, very, very kind of moonshot sort of weird idea, but the reason that I'm compelled to think about this at all, it really just comes from this graph, right? It really just comes from the idea that, I mean, it's not clear whether neural networks are always constrained by how much information they can represent and whatnot. But in general, it feels like you want to use, more than 1/5 of a bit you want to encode more than 1/5 of a bit per dimension. And if you do this, you are forced to use these kind of strategies that to decode require more than just linear plus threshold.
Nice. Mm-hmm.
But then to express computations on the encoded data, you wouldn't be able to just like read out the features and recombine them like people seem to think they're doing.
Yeah.
I mean, I guess there's a sort of a partial analogy there, which would be like how we do computation under homomorphic encryption. So
I thought about the homomorphic encryption stuff. Yeah, these situations where you see the computation happening, but you don't see what the computation is actually doing, right? Yeah, that's also the difference here is that the point is not to obscure, the point is just to have a nicer way to parameterize, the kinds of computation you want.
Yes, that's definitely the disanalogy, right? I'm hoping about the adversarial version of this. Although you could also imagine that under the right training conditions, you could have a network that was maximally difficult to decode, right?
Yeah, that would be good.
I also have another question. Is like some of the inefficiency here, is it? I'm kind of thinking that in the examples, or I don't know if that's the visual look. The things that you were trying to encode are local things like points. And I'm thinking if the things the data distributions or something like that the things that it sees and wants to encode are extremely local things. But if the things that it encodes is like more adapted to the code or something, like, for example, they are disk or something that are something with non-local volumes or something like that, then I'm guessing the distributed code will be like more efficient. So for example, if everything in the signals that the set of signals that I ever see are this of size no smaller than some radius threshold, then I'm guessing the distributed representation will be more efficient than the local one, like per dimension.
If you're trying to encode disks, so things with like low precision, essentially, or like.
So I'm kind of guessing. So if you can encode points, then you can encode anything. But if you don't need to encode everything, so the things that you ever the set of all possible signal in that you will ever see, including in test time, are sort of composed of features that are inherently non-local, like not maximally local, meaning there are no infinitely sharp points and so on. Then I'm guessing that using the distributed representation will actually find you a compression.
Yeah. So that's right. So one explanation, one resolution to this graph is I'm saying, oh wow, like look how inefficient these codes are. Yeah, maybe. I mean, at the very beginning of the presentation, I talked about how distributed coarse codes are pretty efficient if you don't need much accuracy.
Right.
So maybe you're talking about some situation where I'm not really encoding a point. I'm just doing a lossy encoding of a point that lets me read some very coarse features off from it later, or something like that.
Yeah.
Then
the extreme case will be maybe you only ever see sort of points on a certain structure. If you have certain structure and your code is literally lines of those structure, code things as like intersection of those lines, then that code will be much more efficient than being able to encode all possible points.
That's right. Yeah, these codes are good at when you don't have to distinguish too much, when you don't need too much precision.
Yeah.
Right. I'm not sure exactly. There's also some examples in my head about, like in this situation, I don't know, maybe like either the point is in the top left or it's over here, and then my code is very good by default. Yeah.
Any more questions for Chris? If not, thank you again, Chris. Fascinating topic.
Yeah, thanks.
do read the preprint. I think there will be like very interesting references in that.
Oh, which one?
No, I mean your preprints will probably have a lot of like interesting references for us in this. Do you have sort of recommendation for what to read about it?
References. I mean, I enjoyed learning about compressive sensing and whatnot, but it ended up not being that applicable.
Right.
Because I'm studying this regime that in compressive sensing is called like the sublinear regime, where log k is much smaller than log n. And I just wasn't able to find the kinds of like this graph, I wasn't able to find. I found some very sophisticated recent results on like theoretically, these codes are very information efficient in the sense that under, even with Gaussian noise, like the optimal Bayes, predictor is asymptotically efficient or something like this. But I wasn't able to find stuff that really had a direct bearing on these questions. And also keeping in mind that like this example maybe it's a really bad example, right? Maybe the reason I'm thinking that these codes are so inefficient is I'm like thinking about the wrong model. I'm not modeling like 100-dimensional sets of a million elements. I'm thinking about like fuzzy concepts that kind of blend together. Like it's a verb. Like it's very important to know that this token is a verb, and somewhat important to know that it's also somewhat related to dogs and somewhat related to animals, and so that maybe that's another explanation for this information inefficiency thing. And then compressive sensing really doesn't help you at all. So that's why I don't necessarily recommend diving into that.
Right. Yeah. We'll have your preprint. Thank you. Yep. All right. Thanks everyone. Thanks, Chris.
Okay. Thank you.